All right. Thanks everyone for showing up. Um, Today, I'm going to dump a bunch of knowledge on you guys. Um, the point of this is not for you guys to walk away with like a complete understanding of like aerodynamics. People have dedicated their whole lives to this, so that's not my goal today. Um, my goal is to basically give you guys a really good kind of understanding or intuition for how flow fields work and how you consider them when you're talking about rockets. And then my other goal here is to kind of get you introduced to a bunch of different topics. Um, Basically everything from vehicle design to supersonics to 100,000 feet. So give you guys a really broad review of a lot of topics that are relevant to the kind of stuff we need to consider when we're designing rockets, and so that when you guys come back to it later on, you guys are like, well, oh, hey, I've heard of that topic before. Let me read up on it, and I'll come back to you. So, I mean, it comes back to like learning in general, right? What you learn at school is not like you're expected to remember it for the rest of your life. It's more of a, oh, I've heard of that before. I remember doing part of it. Let me go read up on it, and I'll get back to you. So yeah, my goal here is to introduce you guys to a bunch of different topics, give you guys a good understanding of what's going on, develop an intuition, and then hopefully take that into whatever you're designing next. So without further ado, we can begin. So a complete review of amateur rocketry aerodynamics. Almost. There's some stuff I've omitted. Most of it's there. I'm going to yap. Stop me if you have questions. Yeah, feel free to interrupt me. And if you need clarifications on things, just let me know. So we're going to cover a lot of things today. I'm not going to let you guys read all of it, but should be fine. Let's start with like a good understanding of what our rocket actually does, because there's some terminology. We want to talk about things. We want to be on the same page. So essentially, we take off. Once the engine is lit, we're in the boost phase. The boost phase is where we accelerate upwards. That happens for about 10 seconds, and then we're in the coast phase. So at that point, you're just your typical kinematic relationship of a ball going upwards. Same thing. You're only under gravity. You're going to follow a parabola all the way up to apogee, and then you deploy your parachutes and you descend somewhat slower, but it's still kind of a parabola. The area we're considering today is just the launch, just up to apogee, basically. So you have your 10 seconds of hard acceleration and then your 50 seconds of coasting approximately. Those timings obviously change depending on the rocket, how powerful your rocket is, what your target apogee is, those kinds of things that will change. But for us, it's about a minute. So we're talking about a minute's worth of flight time. Some quick concepts and terminology. I'm going to talk a lot about steady state versus instantaneous today. Again, this comes back to like average velocity versus instantaneous velocity. It's the same thing, but you want to develop a mindset that rockets never really reach that steady state. So maybe an airplane, when you're traveling and you're just coasting, you're going a constant speed, the engines are working at a constant rate, you're burning fuel at the same rate, you're not accelerating. You can consider that kind of a steady state, right? There are little variations, but overall, your plane is kind of in the same state for a couple hours, depending how long your flight is. Same thing in a car on the highway. Once you put your cruise control on, you're just kind of in a steady state. You're not accelerating. And so that makes things really easy to analyze, because now your conditions are always the same over time. So you don't have to worry about that time aspect or any variations. You can kind of just take the values at face value and go ahead with your analysis. But in a rocket, we're talking about the span of a minute. You go from subsonic to supersonic, back to subsonic. In that time, you've lost 80% of your atmosphere. You've gone from 20 degrees to negative 40 degrees. Um, there are wind gusts, there is turbulence, there are clouds, there's you're accelerating for part of that, then you're decelerating for part of that. You're never actually at a constant velocity. So you can't really say that a rocket is ever reaching a steady state. Um, and that's really important in your assumptions because any analysis you do has to account for kind of that change in time of all your conditions. And you can never really, like, I might say that the rocket's going to experience 1,000 pounds of axial compression. And that's true for a very, like, 2 seconds in flight. And then it's different. Um, so just something to keep in mind when we're talking here. We're almost always talking about instantaneous things. We're going to talk a lot about flow fields and the behavior of flow in supersonic versus subsonic conditions. All of that we're talking. We're trying to talk about steady states, but in reality, when you're talking about a rocket, that's never really the case. It's always changing all the time. Some quick fluid dynamic concepts to know of before we start talking about actual stuff. Viscosity, pretty straightforward. I think people have a general understanding that oil versus honey versus water, they have different viscosity to it. They flow differently. Some of them are slower. There's a little bit more resistance in honey versus water. It's just kind of referring to the fluid's resistance to change, basically. So, an object has inertia. It's somewhat similar. We call it viscosity. It's described using Greek letter mu. The Reynolds number. Some of you guys have probably heard of this. It's kind of this mysterious number. There's not really a great intuition for it. Doesn't really represent a physical quantity or anything, but it helps us characterize the behavior of the flow. And what it's doing basically is it's comparing on the top the velocity of your fluid to the viscosity of your fluid on the bottom. And so depending on how fast you're going, either the internal viscous forces are dominating your flow or your large-scale velocity forces are dominating the flow. And so what you're going to use this for is that under specific Reynolds numbers, there are ranges to the Reynolds number. Within specific ranges, you're going to be in some type of flow, whether that flow is smooth, laminar flow, or very chaotic flow. That is dependent on how fast your fluid is and how viscous it is. So essentially, what you need to know about the Reynolds number is that it is kind of just a number that's informing you of kind of how the flow is behaving. The Mach number, very important. Lots of you guys know about this. Ratio velocity to speed of sound. We're going to add an extra layer of complexity to it. Your speed of sound is not constant everywhere. It changes depending on your fluid. So, for example, the speed of sound in water is a lot faster than it is in the air. The speed of sound is described using that relationship right there, the square root of gamma RT, where gamma is the specific heat ratio. It's a thermodynamic coefficient. You don't have to worry about it too much. It's 1.4 for the air. R is just your gas constant, and then temperature is your temperature of the fluid. So basically, when we describe Mach numbers, we're actually referring to specific conditions of the fluid as well as just the speed. It's not like if I'm going Mach 1.5, I can be going Mach 1.5 at sea level and Mach 1.5 100 kilometers in the air. And those are very two different speeds. Like kind of just bare bones, those are way different. But because the Mach number represents a lot of the characteristics of the flow as well, you actually know that the properties of the flow are exactly the same. So for example, the friction on my vehicle will cause some heating on the vehicle. that heating, you can be pretty damn sure is going to be about the same whether you're going Mach 1.5 at sea level or Mach 1.5 100 kilometers in the air, because of the fact that the speed of sound is kind of accounting for a lot of the properties of the flow. So this is really powerful because when you want to test something, you can test something in a wind tunnel and recreate the conditions basically just based on the Mach number. So you don't have to worry about like it's really hard to recreate Mach 20 re-entry vehicle conditions on the ground. It's really hard, pretty much impossible. But as long as your flow is Mach 20, it doesn't really matter what the differences in velocities or densities of the flow are. As long as it is Mach 20, what is exhibited by the flow, the kind of those properties, those characteristics that you're trying to analyze are going to be the same. So it's very, very powerful tool. And then the last one is compressibility. So fluids, not very, like liquids, not very compressible. Solids, definitely not compressible. Gases are compressible. Under Mach 0.3, generally we consider them incompressible. That's not really the case, but it's a good assumption. And then at higher speeds, the air becomes a lot more compressible, which will cause kind of increases in drag, increases in heating, and it causes shockwaves. So, yeah. Any questions? Make sense so far? All right. All right. Let's talk about the atmosphere just quickly. The standard model is developed by the U.S. in the 1900s. I don't know, 60s, 50s. Describes the main kind of atmospheric temperature, pressure, density that you might see as a function of altitude. For the purpose of simulating a rocket, using the standard model is generally very acceptable. It gives you the rough relationships between all three of those properties, but obviously on a day-to-day basis, these can change. So, if you're just trying to understand how the rocket might behave like 8-9 months ahead of when you're launching, standard model is completely fine. If you're at a competition, you're simulating the rocket the day of, those small variations can play a role. It's always good to kind of use your local weather stations to actually get those on the ground information about temperature, pressure, density of the atmosphere. Wind, average wind speed increases approximately until 12 kilometers, and then it tapers off. Wind gusts refer to the instantaneous wind speed, and then average wind speed obviously is the average of that. So within some time frame, say a day, you will get an average wind speed, and then you'll have wind gusts, which is like the maximum speed that wind reached. Wind gusts are super relevant on the ground when you're trying to launch a rocket. They can affect your stability a lot. So being able to know in what conditions you can launch the rocket, pretty important. Turbulence kind of refers to the instantaneous movement of the wind. So when you're in an airplane and you get turbulence, a lot of that just comes from pockets of air that are moving in different directions from your average wind speed, causes weird issues, causes variations in the lift of your aircraft. That's why you kind of get those bumpy rides. And then wind direction, something less intuitive, but the wind direction from a meteorological standpoint actually refers to the direction the wind is coming from. So if I say the wind is, coming from 270 degrees, what I actually mean is the wind is going from the west to the east, or from the west to the east, something like that. And then there's a bunch of other local wind phenomena that can impact your flight. Notably, the jet stream in Timmins is quite strong and sometimes will make your rocket drift very far away. So, of course, wherever you're launching your rocket, always important to account for local wind phenomena. Notably, in New Mexico, there's no jet stream, but when we were launching there, it gets super gusty as the day goes by. And we were only able to launch because we analyzed the wind patterns and figured out that there was like 10-minute window where the winds would die down every day. And we knew exactly when that would happen. And so we were able to time basically all of our setup so that we were ready to launch in that 10-minute window, and then it happened, and we launched, and then the range shut down for the rest of the day. So analyzing weather, pretty underrated, but it can be the difference between launching and not. So just some pictures now of what I was describing. So the speed of sound and temperature, you can see the density and pressure functions. So the density and pressure drop off nearly exponentially as a function of altitude. So basically, by the time we make it to about 40,000 feet, there's not much left. So, from a drag standpoint, a lot less drag because the atmosphere is less dense. And then on the left, there's the average wind speed. So you can see there's kind of that big kind of spike around the 10 to 15 kilometer range, and then it kind of slowly drops off. And obviously, maybe the wind starts to increase again once you get up around 30 to 40 kilometers. But if you look at, the density and pressure of your atmosphere, there's nothing left. So the wind is basically non-existent. It's not actually applying any force onto you. So yeah, just some interesting tidbits and things to note. All right, let's talk about flow. So flow versus fluid, they're different. The fluid refers to kind of the stationary kind of gas that you're in. The flow implies that it's moving. So you can describe it, using your velocity, your density, your temperature, your vorticity, which is kind of the rotationality of the flow. So all of those can help describe the flow. You can also, as I mentioned, describe the flow using the Mach number. So the nice thing about the Mach number is that it's dimensionless. So it's not really dependent on your environment because, as I said, you can recreate the same Mach number in many different conditions and observe the same properties. And then the Mach number also accounts for compressibility, right? So if I say the flow is moving at 1,000 meters per second, that doesn't really tell me anything about the temperature of the flow or, the ambient pressure or, how it's moving, or maybe I might be moving at 1,000 meters per second, but I'm still subsonic. If I talk about the flow in terms of its Mach number, then I know if the flow is supersonic or subsonic. You can also talk about pressure as in the static pressure of a fluid. So, for example, there is a pressure in this room, but the air in this room is not moving, so it's just a static pressure. However, when the flow is actually moving, then you can talk about dynamic pressure. So, if you've watched any rocket launch, they will announce that max Q. So they're referring to the maximum dynamic pressure on the vehicle. So that's 1/2 times the density of the flow times the velocity of the flow squared. So it's kind of describing the force or kind of the energy that your flow has. So when they announce maximum dynamic pressure, what that means is you're going through the kind of area of flight where the loads are highest on your vehicle. And then again, you can describe the flow in terms of its Reynolds number as well. So the flow behavior around an object, this is something that you want to make sure you develop a really good intuition for. The flow is going to separate and smoothly part around objects depending on how aerodynamic they are. One assumption we make here is, let's say you have an object in a flow. We assume it's rigid. So it's not moving, it cannot be deformed. Obviously, that's not the case. Rockets can bend. They're kind of like long spaghetti noodles. So there's some flexibility in their designs. Here we assume the object is rigid. In this case, we have an airfoil, and the flow is parting around the airfoil. And since the airfoil in general is quite aerodynamic, you can see the flow is parting quite nicely around the object. However, as the flow velocity increases, basically particles have less time to move out of the way. So if you throw a rock into the water, it will create a wave, and that wave propagates outward at some velocity. The same thing happens in the air. If I perturb a flow, then there is a wave that is sent out. And so similarly here, if I put an object in a flow, then the particles kind of approach the object, see the object, and can move out of the way. And so that's why you see, in subsonic flow specifically, a lot of the objects are rounded because it gives the flow a lot of ease in kind of just moving out of the way. But once you're supersonic, basically you're plowing through the flow faster than the molecules upstream can react. And so instead of letting the flow move around you, you are physically plowing through the flow itself and splitting the flow. So that's why a lot of those supersonic designs are pointy. Just kind of things to note. Here in this picture, you can actually see that the angle at which the airfoil is compared to the flow is quite high. So the flow actually detached from the wing and is kind of doing these rotational vortice type behavior. That's happens when the angle of attack is too high, or basically when the object is not aerodynamic enough. That kind of happens. And so, yeah, speaking of flow separation, basically here that the way the particles smoothly flow around an object is always dependent on small angles of attack. So essentially, angle of attack is kind of the angle at which your object is facing relative to the incoming flow. And so in this case, that angle was too high, and so the flow was not able to smoothly go around the airfoil. Instead, it kind of just went over the hump and then just was like, what do I do? And tried to fill the void that was there by kind of rotating inwards. And this is less than ideal. You lose all your lift. You don't want this to happen, basically. So just some questions here. Where might shockwaves form on this rocket? Does anyone have any ideas of where the shockwave might actually form on this object? Yep.
Like where the cone ends?
At the cone ends? Yep, that's a good idea. Yep. The tip? Yep, also a good idea. Any other locations you think that shockwaves might form?
The back fins.
Back fins, yep. And the canards, the small little fins there. Essentially, any protrusion when you're going supersonic will create shockwaves. They might be small shockwaves or large shockwaves. But yeah, your main shockwave is going to be always at the front of the vehicle. And then any large protrusions after that will create smaller shocks. So yeah, at the junction of the nose to the body, you will also get a smaller shock. You'll get smaller shocks around the canards as well, and you might get a slightly larger shock at the beginning of the fins. And then just some examples of things that can disturb the flow. Any kind of bolt circles or protrusions, like cameras or bolts on the fins, or launch lugs that keep the rocket attached to the rail. All of those are protrusions. They will affect the flow. They're not that big of a deal at the end of the day, but they are there adding drag, disturbing the flow, kind of preventing things from flowing smoothly past the object. Yes?
What causes shockwaves?
What causes shockwaves? I will get to that very soon. Yes. So before we get to that, actually, let's talk about lift and drag. The two main forces on your rocket, actually not really. The main force on your rocket is gravity and thrust. But drag is a big one, lift is less so, but they're still there. Again, the airfoil. Lift is defined as perpendicular to the flow direction, and drag is always parallel to the flow direction, always. There are other conventions you can talk about, such as like normal force, but for now we're just going to talk about lift and drag. It's pretty intuitive. One of you pushes up, one of you pushes against you. Lift is caused by a pressure difference between the top and bottom of an object. So in this case, the airfoil, the shape of the airfoil causes a high pressure region underneath the wing and a low pressure region above the wing. High pressure likes to equalize with low pressure, so it's pushing up, generates lift. Depends on the flow density and flow velocity, so you can see that rho v squared in there. That, again, you can combine it with the 1/2 and get your dynamic pressure, so just swapping around the terms, but depends on your density, your velocity squared, and then the object's surface area and shape. So the surface area, you're just going to take the surface area of the wing, and then the object's shape is kind of combined into this coefficient of lift, that CL value there. That CL value, very mysterious. We just have it in there. Essentially, it can account for changes in lift with angle of attack. It can account for geometries, and it can account for the type of flow, whether you're supersonic or subsonic. So that value is kind of just there to represent a bunch of other variables that can affect how much lift you're generating. But in every single case, it's always proportional to that rho v squared. Yes?
So the surface area, does it depend on the direction of the wing?
No, it's just typically you just take the cross-sectional area of the wing. Yeah. Or whatever object you're actually looking at. So it's not just wings that create lift. All things can create lift depending on how they're positioned in the flow. The rocket body tube actually produces lift. It just depends on how it's facing. And then similarly for drag, it's the same exact equation. We're just replacing the lift coefficient with the drag coefficient. Again, it's accounting for a bunch of different things. And drag obviously resists any kind of motion. It's there as a resisting force, and it's anti-parallel to the main axis. So yeah, any questions with that? Nope. All right. Bernoulli's equation. It's pretty overhyped, but I put it in here because people talk about it all the time. Essentially, all it's saying is that the pressure and dynamic pressure in two different situations is always equal. Kind of the same thing as conservation of mass, but for kind of fluid pressure. Basically, the nice thing about Bernoulli's equation is it's one of those conservation equations. You can combine it with the conservation of mass to explain why your wing actually produces lift. So, I said that there's a high pressure region underneath the wing and a low pressure region above the wing. That difference in pressure causes the wing to move upwards. But we can explain that with Bernoulli's pretty simply. Essentially, if you have, a river, a deep river, it's moving water at some rate along that river. Then at some point you reach a rapid area. It's a much shallower area of the river. So there's essentially less area for the river to go through, right? It's got to move the same amount of mass through a smaller volume. And so what happens is the flow has to accelerate. It has to go faster. So kind of the same thing here at the bottom. You have a much larger area. The flow is moving slowly. And then if that same amount of fluid has to move through a smaller area, it has to accelerate. Pretty intuitive, but it's the same thing here. The shape of this wing basically means that the top surface is longer than the bottom surface. And since the flow has to keep moving at the same speed all the time, then the flow on the top surface has to increase its velocity so that both particles meet at the tail at the same time. And since it has to increase that velocity, then you can see that by this kind of conservation equation here, if your velocity increases, then your pressure decreases. And so that's why if your velocity is moving faster at the top, your pressure is decreased, and so you get that high pressure, low pressure region explains lift. But in general, Bernoulli's equation, you never use it. It's overhyped. Yeah, I don't know why people talk about it so much. I don't know, just exists, but it's not really that important. All right, subsonic flow, and then I'm getting to supersonic flow. So subsonic flow, pretty simple. Everyone's familiar with it. Particles can move smoothly out of the way of an aerodynamic object. So essentially, you can see that in this picture here, the plane is moving subsonic, and so it's generating all of these waves, these propagating waves that are moving at the speed of sound. And since it's moving slower than the speed of sound, those waves have time to move in front of the object and warn all the other little air molecules, hey, by the way, move out of the way, there's an object coming close. We can account for compressibility by using the Prandtl factor. So again, we're just kind of comparing the local Mach number. It'll create a factor that you can add on to your lift coefficient, for example, to account for the compressibility of the air and how that will impact how much lift you're generating or how much drag you're generating. So just something that's typically kind of a correction factor that we add is that Prandtl factor right there. And then, as I had mentioned before, because the air molecules have warning ahead of time that they need to move out of the way, a lot of the designs have these rounded features so that you're letting the air molecules move out of the way very nicely. It creates less drag, and it displaces the flow more smoothly. Yes?
When you say like the air molecules know, they don't like literally know it.
Well, they don't really know, but the wave propagating is just a pressure wave.
Yeah.
And it's a mechanical wave, right?
Yes.
And so mechanical waves work by molecules bumping into other molecules, bumping into other molecules, and you're kind of transferring that momentum across, right? So it's kind of like that, right?
Yeah.
The molecules right at the nose of your vehicle get imparted with some momentum, and they move forward at the speed of sound and smash into other particles, and those smash into other particles, and those smash into more particles. So they are kind of getting a warning through this kind of pressure mechanical wave that's propagating ahead of the vehicle. So that's what I mean by like they have warning because the wave is physically like traveling through them, basically. Kind of just like billiard balls, like pool table balls kind of thing. Yeah. All right, supersonic flow. So quickly, let's make a distinction between supersonic and hypersonic flow. Supersonic is less than Mach 5. Typically, that's kind of the definition we refer to. The reason it's Mach 5 is really just has to do with the amount of thermal energy kind of in the system. So basically, around Mach 5, you're basically going so fast that the literal molecules in the atmosphere start to dissociate. They can create a plasma if you're going really fast and like strip the electrons out of their orbits. So essentially, you're going so fast that there's all of this chemical energy now in that whole mixture. It can create a ton of heating, some really crazy conditions. It's not a really fun area to study. No, it's a fun area to study, trust me, but it's a lot more complicated because of that thermodynamics involved as well. So below Mach 5, typically considered supersonic. That's what we're going to talk about today. I'm happy to chat about hypersonics some other time. Supersonic flow, definitely compressible. We account for that compressibility, again, with the Prandtl factor, but this time notice that the Mach number is flipped. So instead of 1 minus, it's now Mach number minus, just because your Mach number is positive, so you don't want that square root to output a negative imaginary number. So we flip that around. Because the flow cannot move out of the way this time, because they have no warning, the pressure wave that happens when the nose of the vehicle collides with the air molecules around it, that pressure wave is suddenly behind the vehicle because you're moving faster than the speed of sound. And so what that does is you're essentially dragging your waves behind the vehicle in what we call a Mach cone. And so, we call it a Mach cone, we call it a shock wave. It's the same thing, but it's very unintuitive to think about it as literally a cone of pressure. And of course, what is pressure is sound waves. So we hear a bang when a shock wave goes above us, right? But it's only a bang to us because we're standing still. And so the cone just passes over us once, and we hear that bang. But let's say I'm standing still, and there's a plane that's going Mach 1.5 above me. I see the plane first because it's traveling faster than the speed of sound. Then it zooms past me, the Mach cone traveling behind it goes by me, and I hear the bang. And then I start running, and I'm super fast, so I can run at Mach 2 and get in front of the airplane again, and then stop, and then let the whole thing go over me again. I'd hear that bang again. So it's not a single bang that you hear when the plane reaches Mach 1. It's a continuous bang that's being essentially pulled behind the aircraft. So that's one of the reasons why supersonic flight over land is kind of banned across North America, is because of that. It's not just a single bang. It's a bang for literally everyone below the trajectory of the airplane. So just a cool kind of thing to note. But that's also why you don't hear a bang when a rocket lifts off, because the shockwave is traveling upwards, so you don't hear it. But for example, when SpaceX is landing their boosters, now there is a shockwave because it's traveling supersonic, and that shockwave is traveling downwards with the booster, and so that's why you hear it on landing. So as I said, because we're now supersonic, you're slicing through the flow instead of pushing the air molecules around you. So a lot of the designs are going to be very pointy. They're basically trying to slice through the flow as nicely as possible. All right. Any questions on that? Otherwise, we'll talk about shockwaves more because it's cool. All right. So shockwaves, they are basically very thin pressure waves. It's essentially a discontinuity in your flow. So you're traveling supersonic before the shockwave, you hit the shockwave, and then typically you're subsonic after the shockwave. So it's a discontinuity that's basically forcing the air to go back to its normal behavior of flowing at less than the speed of sound. It forms a cone extending outwards from the vehicle. I talked about that. And then depending on the type of shock, the flow can either be supersonic or be subsonic after the shock. So again, referring back to that discontinuity. And then in this example here, we can quantify the angle that that shock wave creates. And so the half angle mu is equal to arc sine of 1 over the Mach number. So essentially, the faster you go, the skinnier this cone becomes. And obviously, you can take this out to infinity, and it technically collapses and all of that weird stuff. But for the purposes of like the Mach numbers we see here on Earth, it's not really possible to go faster than like Mach 30 or something. For those purposes, the cone does get quite skinny. But around Mach 2, that angle is about it's about 30 degrees or so. So it does drop off pretty quickly, but it's pretty cool that we can actually quantify it. Different types of shockwaves. There's a lot of different ones. So the simplest one is a normal shockwave. So essentially exactly perpendicular to the direction of the flow. You don't really see this very often because it requires quite specific conditions. What you're actually going to see are oblique shocks. So again, that oblique refers to that have there being some sort of angle in the shock. You can see on the top here we have two different examples of like slightly pointy objects, and then there's an angle associated to that shock wave. And then these shock waves can either be attached or detached. So what I mean by attached shock wave is that the very front of the shock wave is in contact with your vehicle. So these two top examples here are attached shocks because they are in contact with that very thin pointy wedge in both of these cases. What this results in is a lot of heat conducted into the object. So if your shockwave, which is just a massive, super high pressure region, is in contact with your object, then a lot of that energy from the flow is then being converted into thermal energy inside of your vehicle, and that's what creates a lot of heating. A detached shock, on the other hand, basically these two bottom pictures here, means there's actually some space between the beginning, between the shockwave and the beginning of your vehicle. This is actually a really cool feature because basically, even though that type of shock has more energy in it, a lot less of it is transferred to the vehicle because you have that air cushion between the two. So it's acting kind of as an insulator. And so this happens a lot when you have rounded features and you're traveling supersonic. So another one of these reasons, the rounded feature will add more drag to your vehicle, but that may be advantageous if a lot less of the heat from the shockwave is actually going into your vehicle. Some vehicles do this by design. So all of your re-entry capsules from space, they all have a very rounded, flat surface on the bottom. Essentially, they're making sure the shockwave is detached so that there's a lot less heat that goes into the capsule, and they're producing more drag, so it helps them slow down. So in some cases, that design can actually be doubly beneficial. Obviously, for things like fighter jets, we don't want to generate drag. We want to be as aerodynamic as possible. So then you're just going to have to eat those extra that extra heat that goes into your vehicle. Just some tidbits: you can model the shock standoff distance using the Billig's model. You really don't want to know what it is. It's pretty disgusting theory. But if you want to know, it's there. And then, yeah, I think I've covered most of that. Any questions about this? Yes.
Why do detached shocks occur?
So basically, let's say you're going Mach 2. The shock wants to be an attached shock, and it wants to have some predetermined angle. If you make sure your geometry has its own angle being larger than that shock angle, you are essentially forcing the shockwave to become rounded and detached. So as soon as the shockwave becomes rounded, it will detach from the object. But you basically need to force that to happen. So, for example, on our rocket, we actually round the tip of our fins because we don't want the fins to experience a lot of heating, because if they did, then the epoxy would melt, the carbon fiber would fly off, and your fins are no longer fins, and your rocket is no longer flying. We purposely round them to force the shock structure to be detached. But it really depends on your like design conditions. Like our nose cone, we just make it out of steel, and then the shockwave is attached, right? And so that's beneficial because you have a lot less drag. But yeah, it depends. Like the fin cross section, right, is a lot less area than the area of the rocket. So the added drag from the fins having a detached shockwave is not as bad as the whole rocket having a detached shockwave. Anything? Yeah.
I asked a question. So, like the detached shockwave, the detached shock only occurs when the angle of your cone is greater than the angle of the shockwave.
Yes. Yeah. There's math involved. It's probably not 100% right what I said, but that's the gist of it. Yeah. If you make your object super blunt, basically like super not aerodynamic, then you're essentially forcing the shockwave to detach. So yeah, and actually this is super dependent, I will add. If you actually go look at Billig's model, the radius basically of your kind of contact surface. So they use the radius of whatever your cone or object is to calculate how detached the shockwave is. It's super sensitive to that radius. So even like a difference in like 10 millimeters or like 5 millimeters will greatly affect how much distance there is between the shock and the actual beginning of your vehicle. All right, let's talk about a little bit more advanced shock structure. So oblique shocks propagate at a known angle. I told you that already. They can interfere with other parts of the rocket. So for example, if I have fins on the bottom of the rocket and my vehicle, let's say, is a lot shorter and I'm going super, super fast, then the shockwave from the tip of the rocket might interfere literally with the fins. This is really hard to do, but if you're going fast enough, it can happen. But for example, last year there were concerns that if the canards were lower on the vehicle, that the shockwave from the canards could interfere with the fins. And the shockwave can also kind of interfere with the wing itself. So going back to what I said about how you can force a shockwave to detach if that angle is larger, depending on the sweep angle of that wing. So the sweep is the angle relative to kind of horizontal that the wing is swept backwards. So in this case, it's kind of this angle right here. What this means is that the flow that's approaching your wing is actually slower than the free stream flow. So a little bit of vectors. This is your main vector. The black one is the main vector that's basically showing how the velocity of your flow. Because the wing is swept at an angle, you can actually decompose the span-wise and chord-wise vectors of that flow. And then what you basically get is a slower component of your free stream velocity or your flow velocity that's going over the wing, and that's actually generating lift. Quite complicated, but all it's saying is that if you sweep your wings or your fins backwards, you can make sure that less of that shock structure is actually going to interfere with the wing itself. They do this a lot in military airplanes, fighter jets, because if you sweep the wing backwards, then you can delay the formation of shock waves around your wings, which once you have a shockwave around your wing, causes some issues. You can have flow separation. Sometimes you can have a shockwave on the top of your wing and not on the bottom of your wing. So if you want to delay that from happening, you can sweep your wings backwards, basically. And it means you can still basically be subsonic over your wing, even though the actual speed at which you're traveling is faster than the speed of sound. Yes?
How far does the shockwave propagate?
I mean, it's technically to infinity, right? It's a shockwave, but because it's a mechanical wave, it loses energy over time, so it'll dissipate eventually. For example, like if the plane is traveling, supersonic, but like 100 kilometers above you, you might not hear much on the ground when it passes over you. But it's technically to infinity.
Inverse square law situation.
Maybe, yeah. I don't really know, to be honest. But there's a distance after which you won't really hear it. Yeah. Any questions with this? I know this is a lot more advanced and complicated. Not really tailored to like first year members, but
Basically just saying, sorry, like the darker green oil is the current wing, and then if you were to increase like the angle of it.
So the what it basically is saying is, so the blue line is your wing, the blue is your wing, and the free stream is approaching it. But because the wing is at an angle, only the green vector is the speed you have to consider. And then because the green vector is at an angle now, your airfoil shape is now not the gray one, but the lighter gray one. So it actually changes a little bit the geometry of your airfoil. So for example, here we have like a airfoil, but the shape of this airfoil can change. And there's like a database with tens of thousands of different airfoil types and shapes. NACA airfoils are like a convention used a lot that defines kind of the weight or the shape of the airfoil. So this can be stretched, it can be squashed, it can be like expanded, it can have humps on the bottom and weird different things. So the airfoil shape can change throughout a wing, and it will often be optimized depending on how far out on the wing you are. So that's basically what it's saying, is that essentially the shape of your airfoil now changes because you're taking kind of a diagonal slice of the wing instead of an actual perpendicular slice of the wing. Make sense? All right, expansion waves. This is a fun one. So basically the reverse of a shockwave. In supersonic flow conditions, an expansion of your geometry accelerates your flow. So remember how I talked about the river and how when you decrease the volume that the river can go through, it accelerates the flow. In supersonic cases, this is absolutely the opposite. When you force a supersonic flow from a wider geometry to a smaller geometry, you actually accelerate the flow as long as the flow is traveling at Mach 1 in that kind of throat area. So this is kind of the principle by which rockets and rocket engines work. You have this kind of converging, diverging nozzle. Essentially, your combustion chamber goes boom, bunch of gases are shot out the back. The gases are forced into a smaller area, so it accelerates them because they're subsonic. And they are forced into a volume such that when they get to the throat, they are traveling at Mach 1. And then once you're traveling at Mach 1, you can expand the flow again and cause the flow to accelerate even further. So that's the principle by which rocket engines work. But the same thing happens for shockwaves. So, for example, this photo down here, I have a better picture. So the picture on the left, essentially, you can imagine this airfoil as converging. It's not super obvious, obviously, because there's no like wall on the other side. But you can imagine the flow is being constricted into a slightly smaller area. And so that's why you get a shock there. But then, once you reach the middle of the airfoil, and now the airfoil is slanted the other way, you are essentially expanding the flow. Even though it's not super obvious, but you are expanding the flow. And so what you get is the opposite of a shockwave, which is an expansion fan, we call it. And there's some pretty cool properties involved with the expansion fan. But essentially, it is continuous. It is a kind of pressure gradient continuity across there. So you can actually do some really cool thermodynamics with that area. And then, of course, you get a shockwave at the end of your airfoil as well, because your flow is basically not expanding anymore. So there's that shock there to basically redirect the flow into a straight line, the way it was traveling before the airfoil. So expansion fans, you might be thinking, why does this really apply to a rocket? Well, it applies to active control surfaces. So if you're talking about canards, for example, we flew canards last year, and there was a lot of work done to basically try and understand, when the canards are just pointed straight at no angle of attack, then there will just be a shockwave on them. But as soon as you start to actuate them in different directions, now what you create is the second photo here on the right, where you get a shock and expansion fan pair at both the front and back of your canard. And that can add drag to your vehicle. It can create some funky loads. To be honest, I'm not super familiar with what it actually does, but it's wonky. At the end of the day, expansion fans and shockwaves are just pressure gradients. They're like regions of high or low pressure, but that can, affect the forces on your canards.
Do you want your vehicle shape to be like such that you have an expansion fan? Or no?
I mean, expansion fans are not inherently bad. They occur naturally with shockwaves, but they are a little bit different. Obviously, the shockwave is quite extreme in that, if you get a shockwave interacting with your vehicle, it can actually cause a lot of heating in that specific area. There was a lot of experimental vehicles, in the 70s and 80s and 90s, where they had these basically shocks colliding with other aspects of their vehicle and just like burning holes straight through parts of the vehicle. So you don't like. There's no detriment to having expansion fans, but when you're designing for supersonic vehicles, you do want to be aware of where the shockwaves and expansion fans might be. All right, and then last little bit on supersonic flow, lift and drag in supersonic flow. So remember how I said that the lift equation and the drag equation is dependent on that 1/2 rho v squared, which is your dynamic pressure, and then it's dependent on your area, which is, in theory, not changing between subsonic and supersonic flow. But then your coefficient of lift is changing, and it can change pretty drastically. This lift or drag coefficient is going to, one, account for angle of attack. So often in textbooks, you'll see the coefficient of lift, is 2 pi times the angle of attack. So that helps quantify how much lift you're actually producing if you have a more angled airfoil relative to the flow. It also is a function of Mach number typically. And so you can actually see here, this is taken from last year's design report, but essentially this is me comparing a bunch of different theoretical and semi-empirical models from modeling the lift coefficient based on your Mach number. And so you can see that a lot of these have this like asymptote at Mach 1 because once you create that shock wave, there's a discontinuity there. You have this pressure wave that is kind of really hard to get really good and not just good, but reliable data about that kind of region of flight. So oftentimes you'll see specific lift coefficient models for subsonic and then supersonic cases. And so you can kind of see here that, there's only really one model that is able to model the entire thing, and we don't know how good it is. But yeah, still interesting to see that a lot of these are basically either derived or semi-empirical models that we use to kind of get that lift coefficient. Yes.
Third question. And the Mach number, which one then where's the lift coefficient supposed to? It's like a large or small number?
Sorry, what?
Like when the Mach number reach one, where does the coefficient be like? Is like
Oh.
a large number or small?
So yeah, typically it reaches a slightly larger number. It doesn't go as high as the red or blue line, not nearly as high. This kind of burgundy line is a decent approximation that kind of limits that lift coefficient. But typically, there is either a like bump and then a decrease and then a big increase and then it goes down. But it depends. And the reason it depends is because, as we'll talk about, in the transonic area, so we're talking about this like Mach region between 0.8 and Mach equals 1.3. In this region, you get a lot of drag and a lot of weird things going on because you can basically get formation of a shock wave on one side of your airfoil. So remember how I said that an airfoil accelerates the flow on the top surface relative to the bottom surface. And so that means that when you get close to Mach 1, the flow can accelerate past Mach 1 on the top surface, and it can still be subsonic on the bottom surface. So then you get like a shock wave, basically, that's forming only on one side of the airfoil. And this will really mess with your flow. Maybe it will make the flow very chaotic. But essentially, the flow gets really weird. And so you either will lose lift or you will or you will gain it. So that's why, like, there's not really a good value here. I can't just tell you, oh, it's that, because it always depends on the geometry of your airfoil. So yeah, as I said, weird shock waves, they can cause flow separation in some areas. Realistically, we spend about 1 second of flight in this region. So the TLDR, Ooga Booga Magic Zone, it's about right. We don't really exactly know what happens there. It's quite frustrating, actually, but like literally every single textbook will just give you the model for the subsonic and then give you the model for the supersonic and just not worry about the transonic at all. More recently, there have been improvements. So in the past, so an airplane, obviously it's outlawed. You can't have a supersonic airplane, but you can get pretty close. So in the past, the planes were designed to fly at, Mach 0.8 or Mach 0.7, something where you still aren't generating that shock wave. So you're still not supersonic, but you're getting as close as you can. In recent years, there actually have been developments of like really cool hybrid airfoils that can delay the shock formation, and so you can actually get a lot higher, potentially like Mach 0.85 or Mach 0.9 without generating shocks on your structure. So just a little extra tidbit there. All right. Do you guys want like a 5-minute break, or you guys good to keep going? Good. Raise your hand if you want a break. All right, great. All right, boundary layers. So your flow can either be laminar or turbulent. So I think that's pretty straightforward. Either it's laminar, nice and smooth, or it's kind of very chaotic. Chaotic flow results in more energy losses. It's disorganized. Obviously, it's not as good. In some cases, it is good, but very rarely do we have those trade-offs where it's actually beneficial to have turbulent flow. The boundary layer basically operates on the assumption that there's this no-slip condition at the wall. So what that means is that we assume that a tiny little particle of air that's stuck to the side of your vehicle is not moving any faster than that vehicle. So basically, let's say you have a flat plate that is not moving, and there is air that's moving by at, Lord knows, Mach 1.5 or something. What we assume is that any air that's directly stuck to the wall is not moving at all. So it's the no-slip condition. And basically what that means is it results in this velocity gradient near the wall. So your velocity is 0 at the wall, and then it gradually increases until you get to the general speed of the rest of the flow. And so that boundary layer grows. The thickness of that boundary layer grows by some function depending on if the flow is either laminar or turbulent. So this is where you can bring in the Reynolds number. The Reynolds number obviously is dependent on the velocity of your flow. So you can quantify the Reynolds number at which your flow becomes turbulent. So some cases that you'll see in your fluids dynamic class at some point is that in a pipe, your flow will start out very smooth, and then it will transition very quickly to a chaotic mess. And so if you can quantify, you can do experiments, or try and derive it by yourself, and you can do experiments to try and essentially quantify at what Reynolds number does your flow transition from laminar to turbulent. And then based on that, you can quantify how much does your boundary layer grow, depending on that Reynolds number and how fast you're going and how far down the plate you are, right? So in our rocket, for example, our rocket is 16 feet long. The flow will start off laminar, and eventually at some point it will become turbulent. But that kind of transition to turbulent depends a lot on how smooth the surface is, and how many little bolt circles there are, and how many kind of flow interference paths there are. So essentially, that's why we say, like, it's okay to have cameras and protrusions out of your vehicle, because at the end of the day, it doesn't matter that much. But in terms of transitioning your flow to turbulence, that can actually make a big difference. So, yeah, that's really all I have to say about boundary layers. All right, on to some more like vehicle dynamic stuff. Stability is obviously the name of the game. You want to make sure your vehicle is stable through flight. Otherwise, it'll do a bunch of loop-de-loops and crash and burn quite spectacularly. So there's really 2 points you need to consider. The one of them is obvious. It's the center of gravity. So this is the weighted average of mass distribution in the rocket. So obviously, your rocket has a lot of heavy components. They are spread out throughout the entire vehicle. You can take a weighted average of where they are and how much they weigh, and you can basically determine where all of that mass is concentrated. So if I wanted to balance the whole rocket on a toothpick, where would that toothpick have to be to support the whole rocket? That's the center of gravity. Now, because our rocket is so long, and most of our rocket is actually fuel tanks, that center of gravity for us is typically about halfway down. It depends, obviously. The center of gravity can also change during flight. We're using fuel as we go up in the atmosphere, so that center of gravity will change. But typically, it's around the middle. And so you can kind of, if you consider our vehicle to be a seesaw, for example, then the middle where the seesaw is balanced is your center of gravity, and it's also the point at which the vehicle will rotate around. So if I were to suspend the rocket or something and try to basically use it as a seesaw, then the center of gravity is where I would want to position it so that I can rotate it around that point. The other point that's really important is the center of pressure. So the vehicle, the rocket, as it's going in the atmosphere, it's got a bunch of different forces acting on it. So you have the thrust of the rocket, you have drag, you have lift, you have gravity, you have random wind gusts. You have a bunch of forces that are applying all at different locations on your vehicle. If you take an average of where all of those forces are acting on the rocket, you get the center of pressure. So on a rocket, obviously, let's recall how forces and moments work, right? So you have a force acting on a rigid body. At some distance from the center of mass, it will cause a moment, right? If this is my rocket and I'm pushing at it in the same axis as the center of gravity, nothing happens to it because the force is in line with that center of gravity. But as soon as I act perpendicular or at some distance from that center of gravity, from that rotational point, I induce a moment. So, for example, that's why the thrust, as long as the thrust is in line with the rocket, doesn't really cause the rocket to rotate in any way. However, a wind gust is acting sideways on the rocket, and so it can cause the rocket to rotate. So with that in mind, the center of pressure is where all of those forces are trying to act on the rocket. It's basically like, yeah, if I take all of the forces on the vehicle, they're all like different magnitudes and directions on the vehicle. If I were to sum them all up, take an average of them, that's the center of pressure. So some of the lifting surfaces on our vehicle, what can cause us to rotate? Well, we have fins. Fins are the primary way we keep the rocket stable because they are big flat plates, and since they are flat plates, they're not producing lift when we're pointed straight, right? When we're pointed in the direction as the flow, they are just flat plates. They're not really producing any lift. But as soon as we start to deviate from that direction of the lift, then they will create lift. And so that lift is restoring, basically acting and pushing on the rocket to keep the rocket stable. The rocket body also produces lift, but it's pretty minimal compared to the fins. And so let's quickly discuss the instantaneous behavior of a rocket. As I mentioned, the rocket never reaches a steady state, right? It's always changing. The forces are always changing. The conditions are always changing. For example, the thrust decreases as a function of time. Our gravity is about the same, but our density is getting lower. Our temperature is getting lower. Maybe the wind gusts are getting stronger as we go up. So the forces on the rocket are always changing. That means the position of your center of pressure is also changing. And that means that the rocket is always oscillating. It may not be oscillating a lot. Maybe it's oscillating very slowly, but the rocket is always going to oscillate. And that means that you will always have damping and forcing moments on your vehicle. Essentially, you have forces that are trying to rotate the vehicle and cause it to oscillate faster, and you have forces that are trying to dampen out those oscillations, basically like a spring. Yes?
If you had the center of pressure and the center of gravity at the same point, what would happen?
What would happen? So, I'm getting there. Basically, there are three different cases. You can have the center of pressure above the center of gravity at the same spot, as you asked, and behind it. If the center of pressure is above the center of gravity, that means almost all of the forces on the vehicle are acting in front of the center of gravity, and they're trying to push the vehicle to one side. What happens when this vehicle is at an angle relative to the flow and the center of pressure is up here? That means that all of this airflow is acting at the center of pressure, and since it's already tilted, that airflow is going to want to tilt it even more. Does that make sense? Basically, you have a seesaw, and there's one person sitting on one side, and then you put even more force on that side, causes it to rotate fully. So it's the same thing here. If your center of pressure is above your center of gravity, then the resultant motion is going to cause the rocket to rotate even further, making it unstable. If you have it at the same spot, then you have this neutral stability. So basically, all it means is that whatever angle your rocket is at, it will kind of neither get better or worse. It'll kind of just stay there. This is called neutral stability. In controls, it's also it's referred to as something else. I can't remember. But basically, all this means is that let's say you have an airplane that is neutrally stable, and you hit a gust of wind, for example, and now the airplane is pointed at a 10-degree angle. It will just continue at a 10-degree angle. So what you really want is your center of pressure to be behind your center of gravity, so that if there is anything that causes the rocket to point or adjust its course and be at an angle relative to the flow, then the resulting forces will actually push the rocket back straight into its normal position. So that is what we call a rocket being stable. It is, you want to make sure the center of pressure is always behind the center of gravity. So how do we quantify stability? You can do this in a few ways, but the best way or the most common way to do it it's not the best way, but it's the most common way to do it, is the static stability margin. Essentially, we measure and quantify the separation between your center of gravity and your center of pressure. And we do this by measuring this in calibers. So a caliber, as I wrote here, is 1 times the diameter of your rocket. So in our case, a caliber is 8 inches because our rocket diameter is 8 inches. We can also measure it as a stability. We can also measure it as a percentage, basically. So if you take that separation divided by the length of the vehicle times 100%, you can also quantify your stability as a percentage. But, off the bat, in my experience, you want to make sure your minimum stability is always above 1.5 calibers. Almost every single competition will require this, and then your off-rail stability, basically your initial stability as you clear the rail, should be above 2. And it's possible to be overstable. You can, if your caliber is like over 6 to 8 calibers, then you can be overstable. Nothing really bad will happen, but this is controlling how quickly your oscillations are dampened out. And typically you don't want, if you're overstable, you're dampening those oscillations quite quickly. You typically don't want that. Some things to keep in mind about static stability. The center of gravity and the center of pressure both move during the flight. And the center of pressure actually typically moves forward in the supersonic regime. So once you're supersonic, the center of pressure actually moves forward and makes your stability worse. All right, fin design. So the fins obviously are the main method of providing stability to your rocket. And there's a few different parameters that I can show you that will help quantify or kind of design a fin. You have the root chord, obviously, the tip chord, the semi-span, which is the width of the fin, the leading edge, the trailing edge, the sweep angle. I want to talk about fin design in terms of trade-offs because there's a lot of them and they're always at odds with each other. The first trade-off is stability versus altitude. The more stable you make your fins, i.e. the bigger they are, the more drag you produce on the rocket. And so you typically don't get as high as you could if your fins are more stable. You can sweep the fins. So if you increase the sweep angle, then you can reduce some of that drag because they're more aerodynamic. So it's a little bit of a middle ground. But typically, yeah, if you want your rocket to be more stable, you won't go as high. Obviously, you don't want to design your fins so that you're exactly at the minimum stability you need to be safe. That's not a good idea because things always change and your simulations are almost never perfectly accurate. So you want to design with some buffer there. But yeah, typically you're going to be at odds with stability versus altitude. Another trade-off you might have is semi-span versus fin flutter. So one of the easiest ways to make your vehicle more stable is to increase the width of your fin. So the semi-span of your fin, if you make that bigger, it's by far the easiest way to make your rocket more stable. However, the longer or the wider your fin is, the more you decrease the fin flutter velocity, which is something I'll talk about later. But essentially, you can't make your fin just infinitely wide because then your fin gets really, really weak and susceptible to vibrations, and that can destroy your fin. So there's always that trade-off. Oftentimes you'll look at how fast you expect to be traveling, and then based on that, you'll kind of establish what the maximum width of your fin can be. Another trade-off is the sweep angle versus fin flutter. So as I mentioned, you might be tempted to sweep your fin back more to gain more altitude and still be stable. But again, by sweeping the fin backwards, then you are making the geometry more, how to say, like asymmetrical, and this can also make their fin less strong. And then lastly, you can talk about manufacturing versus optimization. Oftentimes, the best fins aren't the most easy ones to make. And so simple geometries and cross sections are often a lot more prioritized in model rocketry because they're easy to make, but they're not always the most optimized. So for example, our fins, they actually just have a plain rounded cross section. We don't actually do anything to the cross section. It's just a rectangle. But if we really wanted to optimize this, then we would develop a airfoil shape for them to kind of see which would get us a lot less drag on the vehicle. But then obviously those are a lot harder to make. All right, let's talk about some active control surfaces. So just briefly, I'm just going to talk about what they are and how they work. There's a few different main ways you can control a vehicle actively during flight if you want to. The first way is what we did, which is canards or any other actuated surface. The canards can be wherever you want on a vehicle, and they will probably still work. But they work by obviously controlling their angle, which creates some lift, and that lift causes the rocket to either roll, yaw, or pitch in some direction. And then obviously you have to account for their positioning on the rocket, which will affect their stability of the stability of the rocket overall. So yeah, a little nice picture of what we did. You can also spin stabilize your rocket, which is a really cool way of doing it. Basically, it's using conservation of angular momentum. You can spin up your rocket really fast, and if you get it up to a given speed that you can calculate, basically it becomes really stable because any external forces on it, have to, you're using basically the angular momentum of the vehicle to prevent any deviations. Similarly to how a football is, spun really quickly to make sure it doesn't go in weird places. And then same with bullets, for example. So bullets are basically shaped so that they spin, and that's why they go in a straight line and they don't go all over the place. So yeah, really cool method, but you have to have careful consideration for recovery deployment. So essentially, your rocket can't be spinning when you deploy your parachute, because then you tangle your parachutes, and then you're going to fall ballistic. And then lastly, thrust vector control. Very difficult, very complex to do, but arguably one of the best ways of controlling your vehicle. You can control it based on either some sort of gas injection into the nozzle or gimbaling or mechanical systems to control the vector thrust of your engine. All right, last section, we're going to talk about potential destructive aerodynamic phenomena. So basically really weird aerodynamic things that can happen that can basically completely destroy your vehicle. And the first one is coning. So coning is the coupling of your roll rate and your pitch oscillations. So your rocket might be spinning at some speed during flight, and as I mentioned, the rocket is always oscillating during flight. If those two rates line up or are approximately equal, then they will amplify themselves and cause the rocket to essentially rotate on an angle, and that corkscrew motion will increase until the rocket self-destructs. So you can actually see here, this is literally a screenshot from a video that Thomas sent in channel, where you can basically see really clearly the plume slowly start to develop these oscillations, this corkscrew motion, and then it blows up. And obviously I took a screenshot so you don't actually see it blow up. But basically, this can be caused for a lot of different reasons. If you accidentally manufacture your fins and there's some weird angles in them, then that can just cause your rocket to spin up really quickly. You can also have an active control failure. So let's say your canards accidentally go to its maximum position in the same direction, or they start going in the same direction and start pitching the vehicle over. They can induce coning effects in the rocket quite significantly. So when you're designing a rocket, a few parameters that you want to look into is the natural frequency of the rocket. The natural frequency will determine oftentimes how quickly you're oscillating back and forth. And then the longitudinal moment of inertia and the rotational moment of inertia will determine also how quickly you can roll and how quickly you can pitch your vehicle. And you're going to want to make sure that those have been kind of properly analyzed to make sure this is not something that will happen. Because trust me, this is not fun to watch. The second really weird aerodynamic phenomena that you might encounter is roll reversal. So essentially, a wing is creating lift because there is a high pressure underneath and a low pressure underneath. Now, if the wing extends to infinity, then you just have a super long high pressure region and a super long low region. But because the wings are finite, basically you can get pressure, high pressure from underneath the wing, trying to compensate and go to the other side of the wing, so to kind of re-equilibrate both sides, the pressure on both sides. It's going to try and go around the tip of the wing. And in doing so, it causes rotation in your flow. And so that rotation is a vortice that grows behind the wing. So you can see it starts out really small and curled. And then as you go behind the wing, it increases in size. And what that can do is if you have your canards in front of your fins, that rotation, kind of rotational flow, can impact the fins and cause the fins to rotate the opposite way. So essentially, you're commanding your active control system to rotate the vehicle one way, and instead you get opposite rotation. This happened for quite a while on missiles, because missiles need to be super, they need to have a lot of maneuverability, right? So they need to be very, very good at turning very quickly in flight. So they had canards that were really, really big, and then they were running into issues where the interference between those canards would impact the fins at the back of the vehicle. This is really hard to prove. It's really hard to determine if this is going to happen or not. And unfortunately, because of that, you often have to err on the side of caution because you don't want this to be the reason your rocket fails. So this can be mitigated either with really good simulations and controller development. So, if you test your system really, really well and test for all kinds of weird cases, then you can be really good at identifying when this happens and then preventing it. Or you can make a spin can, basically have your fins rotate freely from your rocket. And what that means is that if the fins are impacted by the vorticity from these wingtip vortices, then it will just cause the fins to spin and not the rest of the rocket. Yeah. Fin flutter. Second to last thing. Fin flutter is really wonky. Basically, it's an aeroelastic phenomenon. So the same way a guitar string will vibrate, and it'll vibrate at some fixed frequency, basically. It produces a single note depending on how it's tuned. Your fin is kind of the same way in the sense that, like, for example, any wind instrument, specifically a saxophone, there is a piece of bamboo in it that's very thin, and when you blow, you are essentially vibrating that piece of bamboo, and then the vibrations are amplifying the sound through the saxophone, right? So the same thing can kind of happen to your fins. If you're going fast enough, your fin is just a flat plate. It can start to vibrate, and if it vibrates fast enough, it will amplify itself and destroy the fins. It's also kind of a weird torsional phenomenon. So you can see here in these pictures, the fin actually kind of torsions itself about kind of a central axis or something. And so this is dependent a lot on how strong your fins are, so how stiff they are, the geometry of your fins as well, and the flow velocity and density, obviously, so how fast you're going. Essentially, what you're going to do is calculate for the thickness and strength of the fin you have, how fast you need to go before this flutter phenomenon will happen. Unfortunately, there's not a lot of literature on this because most of it is protected by government. So what most people end up using is a model developed by Martin from a paper in 1958. It's from NASA. He was a really smart dude, developed a model. Unfortunately, it's quite conservative. It's not super accurate at high speeds, and it makes a lot of assumptions. So that is the kind of model that a lot of teams use. We kind of use it, but we also kind of don't. This is a phenomenon with a lot of destructive potential that you have to, unfortunately, be kind of wary of and just kind of design things to be more conservative than you think they need to be. And then lastly, you can have drag separation. Drag separation is also really interesting. Essentially, nose cones are, one of the most aerodynamic components on the vehicle. They're designed specifically to be aerodynamic, to push wind or push the flow out of the way. And so that means the drag on the nose cones is a lot smaller than the drag on the rest of the rocket. And coupled with this, nose cones are typically a point of separation for parachutes. So if you're going to deploy a parachute, oftentimes you pop off the nose cone and the parachute comes out. What this means is that the nose cones are sometimes not well attached to the vehicle. And if that's the case, once the motor burns out, you essentially have both components with some amount of momentum. And if whatever retention mechanism there breaks, the nose cone can literally separate from the vehicle because there is less drag on it than the rest of the vehicle. And so the rest of the vehicle will be slowed down faster than the nose cone. And obviously this is not good. You'll pop the nose cone, chutes are going to come out early, probably is going to shred the vehicle, things are going to be ugly, blah-di-da-di-da. Not something we want to do. So essentially there's math involved that you can do to figure this out. It's just typically just a force balance that you can do, but this is something you have to account for, especially if your nose cone is quite heavy. This is something that can happen. So overall, couple different aerodynamic phenomena. This concludes my presentation. I recognize there's a lot of knowledge here. A lot of it you'll probably just not remember. That's totally okay. That's why I recorded this. That's why the slides are on the Google Drive. Are there any questions? Yes.
For the weather forecast, because you mentioned when you launch the rocket, you need to know about like the wind speed and stuff.
Yeah.
Are they measuring in real time and convert it in real time?
Yep. Yeah, we have an anemometer on the pad that's measuring the wind speeds at the pad so that we can make sure that we're not launching into a wind gust that's particularly strong and that might affect the stability of the rocket. Yeah. Yes.
Did you learn this from like a course or just mostly on your own?
Mostly on my own, a couple through co-op, curiosity in general, accumulated knowledge from past leads. This is also my area of interest, so there's a lot I do on my own. Yeah. All right then. if there are no more questions, let me quickly check what's up online. Hey, Luca, was this meeting recorded? Yes, it is recorded. I will be up shortly on the drive. All right, then. If there aren't any more questions, then everyone can leave. Thank you very much for attending. Let me know if there's any questions you have later on, or if there's interest in more detailed presentations or things like that. I am happy to talk about more detailed stuff. And yeah, I hope you guys learned something. You have like a better intuition for how all of this works, how you can kind of try to picture flow around a vehicle, and kind of what considerations to account for when designing a rocket. Yeah. All right. Thanks, guys.